Welcome to the Clima podcast. In this episode, I speak to Jason Quinn, Director of Sustainable Engineering based in Wellington. Jason is literally a rocket scientist, but apparently building science can be even more challenging. In this episode, we discuss the topical subject of overheating. Clima inspires and educates people to create healthy, durable and energy-efficient buildings to live, learn, work and play in. All right, Jason, now welcome here today. It's really great to have you. Now, you actually are a rocket scientist. You worked at NASA, didn't you? So tell us a bit about that.
Well, it's a funny story. I guess I was a rocket scientist. Might be more accurate to say that these days because it's been well over a decade now. And, I had a pretty typical boyhood, I think, when I grew up in the United States. And always wanted to work at NASA and do rocket stuff. As a kid, that seems exciting. And so I worked at NASA for a little over a decade at NASA Marshall Space Flight Center in Huntsville, Alabama. So that's where I worked. I got that job there because I had quite a bit of background in hypersonics, so above Mach 5 kind of vehicles and rockets. And they were hiring folks that had those sort of expertise at the time to work on a program. So I worked there for, like I said, a little over 10 years. And amazing place to work in almost every way except for fulfillment of job done. So effectively what happened was I worked on several programs for a space shuttle. And they just kept throwing them away and deciding to do something different every few years. And I realized I could get through my entire career and never have done anything, really, is kind of how I felt at the time. And I had a young son, brand new son at the time. And I was like, do I really believe in climate change? Like, how am I going to look at him in 20 years and be like, hey, I did these rockets that never got built and good luck. So I decided that I'd quit and move overseas. And that's what I did.
What was it about New Zealand that brought you here?
I'd been here on a honeymoon for 3 months. So it was really the only place I'd been outside the United States, except for a few shorter trips. And I just wanted to come somewhere and kind of figure out what I want to do the rest of my life. So my wife at the time and we agreed to move to New Zealand and try it out. And New Zealand offered us residency and health insurance and a nice place to sit and think. And so it's been great.
What is the purpose and the goal of your business, Sustainable Energy?
Sustainable engineering.
Engineering, Mom.
Yeah, no worries. So the purpose of our business is to apply building science at scale to improve buildings in New Zealand. That's the simplest way to put it. And so we've got a team of 6 technical staff now, and we do primarily energy modeling and other building physics stuff like moisture modeling or air tightness testing, all that sort of things you do around buildings to understand how they work and how to make them better. I don't want to get too much into it, but there's the building code in New Zealand can use a lot of improvements, and as well as the way we build buildings. And the science is pretty clear. It's available overseas and here as well. So that's what we're trying to do.
We're seeing a lot in the media at the moment about overheating of our homes. Why do you think this is such a big problem here in New Zealand?
I think it's probably more of a problem in other places, but certainly in the media in New Zealand makes it seem like it's a big problem just to New Zealand. But there's more overheating problems in the United States and like Midwestern states, and in certainly UK, London's a classic case study, right? But the reason it's become a problem in New Zealand primarily, in my opinion, is because of design initiatives or styles, I guess I want to say that, in new homes. So it's a combination of, for detached single-family homes, it's design style, pretty much is what I'd say is the main issue. And then for smaller things like apartments and such, it's just limitations of the way the buildings are designed. And they're not modeled, so they're designed by, I don't want to say complete guesswork, but in terms of thermal performance, complete guesswork is a reasonable way to say it. There's no thought at all for thermal performance. There's just, do I meet the legal minimum to build the building or not? Is really the only thing that's looked at.
Can you just go a little bit deeper into that? So currently we work on something called the schedule method, don't we? Can you just explain how that works?
So the schedule method in New Zealand, and there's other countries that use it as well, it basically is a list. So it says your walls have to be this good, your windows have to be like this, your roof has to be like this. And if you do those things, you legally can build a building. And the schedule method had limits. So if you build a building with windows over a certain percentage of the wall size, then you have to go to either the calculation method or the modeling method. And the calculation method, you basically look at averages. So like you average your window and wall, and if you have bigger windows than you're allowed to under the schedule method, then you're going to make the wall or the roof better to compensate. But all those things just look at heating demand. they're all inherently looking at heating loss to some level, and they don't look at how the building works in the site or the building shape. Inherently, schedule methods or the calculation or modeling method, all three of them we use in New Zealand, inherently award designers for really inefficient designs. So if you build a building that's compact and efficient, it's going to perform much better if you use a schedule method because it has the same constructions as one that's really big and inefficient. But if you want to make a building that's big and inefficient meet the modeling method, it's much easier because we use something called a reference building. Basically, you model the building in a computer as you're going to build it, and then you model the one that would meet the schedule method and compare the two. So a building that's really inefficiently designed, like really stretched out long hallways and everything, it's easier to make it meet that method and be allowed to be built than one that's more efficiently designed. There's a lot of other things around that.
So recently, obviously, the H1 energy efficiency has been updated, and people are saying, well, this must be due to the fact that we're now putting insulation in, that we're locking the heat in. What are your thoughts about that?
It's like if you're outside with a ski jacket and you can take the jacket off, do you overheat in the summer? No, you just take the jacket off and you're fine. And people draw this parallel like, well, the house, it can't take the jacket off. No, but it can open the windows up. So the only case where you can show that more insulation makes the building worse, the only practical case, is when you can't ventilate. So if the building closed up, then in the computer you can say, oh, a building with more insulation is slightly worse. But the reality is that in general, more insulation is better to keep the building not to overheat. Because if you have a building you ventilate at night when it's cool, and then in Auckland or Christchurch when it's hot in the middle of the day, you close the house up and it goes through the middle peak, and you open up again at night. I think every publication that MB's done since the release has said that we've looked and we've made sure the insulation does not make the problem worse. It's just something people say. Now, we do have a lot of new buildings that are built with the new insulation standard, and they're built with a design style that has lots and lots of glass, especially in the main living areas. And because they're not modeled, they're just kind of sketched on paper to look nice and beautiful, and they often are. They do tend to overheat quite a bit, but that's poor design, not because there's more insulation.
In my preparation for this interview today, Jason, I came across a brand's summer overheating study that was done back in 2000. And there's all sorts of factors that they talk about in that study. They talk about the physical and the physiological factors, including air temperature, mean radiant temperature, air velocity, humidity, clothing, activity levels, all sorts of things. Perhaps you can just delve into a couple of those and give us some feedback of what you think. We've had a brief look at that study together now. Well, what do you think of that study, and what people could take from that study as useful information, and perhaps what's not so useful?
Yeah, I mean, let's talk about thermal comfort. We've got all these factors, and you just list them all, that kind of impact the human in the building space to feel overheated or not. And those things are nice because you measure all those things when you're doing research studies. And the more complex computer models can tell you all those things for a space. But the reality is that what you need to know is somebody comfortable or uncomfortable in a space. So there's combinations of all those factors that yield kind of comfort zones and discomfort zones. I guess think about that. The point I want to make is that for you and I, we're different people. So we can be in a space and I can be too hot and you can be comfortable, and vice versa. And if I'm working, lifting stuff, I'm stacking shelves, and you're sitting down, I could be comfortable and you could be cold. That's just part of the reality. All those fancy parameters in those studies are just ways to quantify those different things so we can measure them and compare across different climates and space. They're not terribly useful when you're trying to talk to a real person about overheating in their home. They are useful when you're looking at cooling strategies. Like, so if you have a climate that cools down at night, like Christchurch, it's often it cools down at night, then night ventilation is a great strategy to control overheating. You night ventilate, insulate the building really well, and then you close it up when you go to work, and you come home, it's still not overheated if it's well shaded. And then you open the house back up again, and you don't even really need air conditioning, you'll be fine. In another climate, which is really humid and hot at night, Jeddah in the Middle East, right? It's like 40 C and smoking hot all the time, and it's always 100% RA. So they can't use night ventilation. It just doesn't work. They can use night sky radiation, but they pretty much have to air condition. So that study we looked at, and you're right, we just look at it very briefly. And the study looked at lots of parameters with an interesting computer model. And the issue I've got with most of those studies is that they need to come up with things that people can do to the designs and provide those design guides to people. Otherwise, they're really only useful for that specific case. So if you look at a computer model for a building and they're like, hey, what worked on this building best was window coatings, let's say. That might be because they have a western-facing facade and they can't use external shading on that building, and that's the solution they came to. But it's hard to generalize that across other buildings.
When we have a look at Passive House, they quantify 25 degrees as sort of the break point between overheating and not. So anything over 25 degrees is seen as overheating. And they give a percentage of 10% per annum as the maximum. How useful is that?
Honestly, not very useful. So it is useful to the designer because they can see this building's overheating 10%, and we teach those classes, right? One of the things sustainable engineering does is we do the Certified Passive House Tradesperson training, and a year from now we'll be doing the Certified Passive House Designer training as well, because FANS is going to combine with sustainable engineering, so the Passive House Academy New Zealand. So what we teach our students and what Cara has taught for many years now, Dr. Cara Rosemeyer, when she teaches Passive House, is that 10 degrees is crazy high. So the reason I said it's not very useful is that you have to know what the hell's in the Passive House planning package. So assuming they've modeled the house the way you're going to build it on the site with the right shading, and they've used something called Design pH, which does the sun angles correctly, so they're actually showing the right amount of sun into the building. So they've done everything they can as a Passive House designer correctly. So then that 10% is useful for them to look at what changes they can make in the building. And typically an experienced Passive House designer will want to drive it down to less than 1% if you're not going to put cooling in. Typically, if we're at 5% with a bunch of conservatism built in the model, like we've turned all the knobs up to it's going to make it overheat almost on purpose, then we'll tell the client, well, it's okay to not put cooling in, but we really recommend you wire for it and plumb for it because you may want to put cooling in later. The reality is, in a passive house or a very well-designed high-performance building, you don't need much cooling. Like basically you're compensating for the sunlight coming in the windows and the internal heat gains of the people, right? Because the rest of the envelope's really well insulated. So you're getting no heat through the walls and roofs and floors. So the amount of cooling you need is actually quite small. Now, the issue you have with Passive House Planning Package is that when you've done that 10% overheating, you will then often use that to predict the cooling loads you need for the building. And that overheating prediction is with whatever you put in. So if the designers put in that you're going to use night ventilation and you don't night ventilate because it's noisy on the road outside and you don't want the kids to wake up, and it's nice and quiet in your house if you shut the windows because they're triple glazed in Christchurch, then you can get a building that overheats now. So I had a building that we certified. We didn't design it in Christchurch. And so it was a certified passive house, relatively balanced glazing ratio. I would say is a very good design. And client called me up about midway through the summer. And she's like, it's been 25 fucking degrees in my house for 3 months or something like that, right? And I'm like, oh, that's not even overheating yet. It's 0%. And what happened is she had a house that was designed to a very low percentage for overheating. However, it had higher internal loads than the designer expected. But the big difference is that in the model, the designer had night ventilation. And in Christchurch, that's very effective for overheating protection to reduce the overheating of the building. And after they lived in it in the winter, they loved the winter because it was nice and warm throughout the house all the time, right? Beautiful, quiet. They open the windows and it's noisy outside because there's traffic. And they want their daughters to sleep at night. You know how important it is for young children to sleep, right? For your sanity. So they shut the windows. And now the building doesn't have night ventilation. And it overheated much more than they intended. And the clients they were asked to put a heat pump in. They were told they should put one in just for safety. And they did not want to because they just didn't like heat pumps. They're just philosophically opposed. I think we should have just put one anyways, not told them, and just put it behind a bulkhead somewhere. But that's, I don't get my wish sometimes. We fixed that by adding additional external shading on that building. Or rather, I recommended they do that. I don't know what they actually did, but they didn't complain anymore. So the problem with any of these computer models is you need to actually put in what you're going to have in the building. So in this particular example, the client and the designer had different perspectives on how the building was going to work. And it's very possible the client initially said they were going to night ventilate, but once they were in the building, they didn't want to anymore.
Talking about ventilation, now we're talking about windows, aren't we? Opening windows. Currently, we have a building code that requires 5% openable window space. How well does that work when we've got window stays, if it's a double story? How do we actually achieve that ventilation?
So is it 5% of floor area? I think it is.
I believe so, yeah.
Yeah, that's right. So 5% of floor area is openable, and then they don't count the fact that you've got security stays, right?
Yeah.
So they pretend the window can fully open when they count that 5%.
That's what I'm assuming, yeah.
That's what I've seen in practice, yes. So let me just take a step back and talk about overheating. The easiest way to think about overheating in a building when you're designing it or living in it, it's kind of like a seesaw. So you got a seesaw. On one side, you've got things that make the building hotter. On the other side, you got things that make it cooler. So on the hotter side, you got like sunlight entry through windows. That's pretty much number one. Then you got internal gains. and then you might have a little bit coming through the solid enclosure, depending how good or bad your insulation is, right? So for an old villa with no insulation on the roof, you got a lot of heat through the roof. But a modern house, not so much. And then in the cooling things, you got natural ventilation, you got heat loss through everything else, and then you've got basically cooling you pay for. If you've got a building that's got a lot of heat gain, like it's got a west-facing facade, and you don't have any external shading on those windows, and you don't have glass that's designed to keep the heat out, then you need a lot of natural ventilation to control that heat. And 5% is probably not enough in a lot of cases, especially if you've only got single-sided ventilation. You don't have ventilation go through the building and out, or in one floor and then up a floor and then out again. Both those are really effective. You know, if you're trying to look at, is 5% enough? No, even if it was 5%. And you're right, once you put window stays, you don't. One of my staff told me, sad story, but it was said sort of jokingly, unfortunately. We worked on an apartment building in Wellington. It's a new building, and it's got cooling in every unit. And one of the sales pitches apparently is it won't kill your pets, because we've had a couple pets die in Wellington recently where they had apartments that had a lot of west glass. They only had windows and window stays. They left work with the windows open, expecting the apartment to stay cool enough, and the dog died of heat stress. So the sales pitch for that apartment is now, it won't kill your pets, which is a bit sad, because we've not only got pets, but people living in those apartments.
So there's definitely some limitations around ventilation. Now, what about shading? You spoke about shading glass. How do we actually do that? And, you know, how easy it is, how expensive is it to create shading?
External shading is what we're talking about, so let's start with that. Or external shading of glass, you want to protect glass from direct sunlight hitting it in the summer, effectively. So if you were somewhere near the equator, you'd want shading that extended, maybe a couple meters behind the building in all directions, right? Keep the whole building in the shade. In New Zealand, because we're south of the equator, the sun's to our north, so only the north face of the building can be protected by overhangs. So overhangs on the east and west sides and on the south side don't work. They're just for decoration. To keep the rain off, if you get a nice deep overhang for a useful porch, it's nice. But even a 3-meter overhang on a west-facing facade does bugger all. So when I put together the first version of Echo for New Zealand Green Building Council, I did the first version in the spreadsheet, and they've since gone on and put it online in Python and made it even better. But that first version, was a lot of negotiation about how much detail you put in, because that's a simplified energy model. I insisted and built in for no additional cost the overhangs. And the main reason I did that wasn't to make the sun entry into Echo better, because it's actually, I prefer they use design pH. But it was to allow architects to see that if they're building with a north facade, plus or minus 15 degrees, overhangs work wonderfully to keep the sun off those windows in the summer and let the sun in the winter. But on the east, or windows that are faced 45 degrees west of north, it doesn't do anything. And you need basically either sliding shutters or vertical shading over the windows, right, which blocks the view to some level. So external shading works great on the north side with overhangs. Everything else, you've got to have some sort of cloth or barrier else. That's just a limitation of the physics of the way sunlight works. So when we're talking external shading, unless you've got something that blocks the sun off the glass, that's what you want. You want it on the outside and it wants to block the sun. So you can have sliding shutters. So I've got a neighbor that's got a nice sliding shutter over her main window that window faces north because she doesn't have overhangs. So she slides it in place for the summer months, and then she pulls it back and locks it in place in the winter months. She only does that seasonally. And that drastically changes the temperature in her house and prevents overheating in that building quite a bit. So that's external shading. When we look at that seesaw, again, we're talking about sun entry through windows is the kind of thing that makes it hot. And the way you reduce sun entry in a window is one, external shading. And that is, for overhangs, is incredibly cost effective because they're fixed, they don't move. For any other window, east and west, you pretty much need things that move. If you've got a single-story home, solar sails work really well, even shade cloth. Or once upon a time, had a building with way too much west-facing glass, and I grew beans up it one year on strings, right? Which is very hippie and cute and way too labor-intensive. I'm not much into gardening, sorry. So anything you can do to keep the sun off the glass will work quite effectively. And then you have the glass itself. I don't know if you want to talk about that here or not.
Let's talk about the glass, because I'm quite interested to delve into, there's a lot of talk about these coatings, low E coatings and things, and how those affect the cutting out of the sun in the summer, but also then what does that do in the winter for obviously the solar gains that we want to have to minimize our heating.
So let's again start from that seesaw, right? So you got seesaw on the side that's gaining heat into the building. You've got sun entry through the glass. So it's not just sunlight hitting the window, but it's what comes through into the house and stays in the house. First of all, we should talk about glass. So people may not realize this, but we don't make glass in New Zealand. And we make like decorative glass, but we don't make window glass for buildings in New Zealand. It's all imported. And then we make the double glazed units, mostly make the double glazed units, so triple glazed units here in New Zealand. Some glass is imported already as triple glazed units, but it's relatively unusual. Usually in that case, they're in window frames. And glass is, it's pretty much the rocket science in buildings. So glass and coatings are literally rocket science. So a lot of these coatings were developed for the space program originally. So if you think about a low E coating, it stands for low emissivity. When you have an electric bar heater and you see it glowing red and you can feel the heat with your hands coming off that bar, so that bar is emitting heat, that's emissivity, and it has high emissivity, so it lets the heat out easily. But you can make that bar out of different materials. The ones you want to make it out of high emissivity, they let the heat out easily. But you can make it ones that are low emissivity, like galvanized steel is low emissivity. And that means that when it gets hot, it doesn't radiate the heat away as easily. It's just a ratio, effectively. So these low E coatings are metal that's been literally sprayed on the glass, molecular thin. And that when you look out a low E window, you're literally looking through metal. Well, solid metal, but it's just so thin you can look through it. So these low E coatings can have different kind of properties, and they range from old-fashioned pyrolytic low E coatings, and that means that the low E coating was put on at the factory where the glass was still molten, so it kind of gets down into the glass surface. You can't scratch it off. It's pretty cool. If you look at 80s buildings in New Zealand, you'll see some that look pearlescent, like they kind of shimmer in different colors. And that's a low E coating on the outside of the glass. And it's doing absolutely nothing for energy consumption or shading. It just looks good. Whereas if you flip that glass around and put the low E coating on the inside, it would actually make the glass more insulating. But it was done on the outside for looks anyways. And then you have what they call soft low E coats. And soft low E coats have to be between 2 panes of glass or 3 panes of glass, because you can literally scratch them off with your fingernail, or you can get a fingerprint on them. And the glass industry spends a lot of money throwing away glass units that they've made where there's a fingerprint or a scratch in that coating, and the window supplier usually will look at them and say, oh, that one's not good enough, give me another one. But these coatings can be adjusted so you can change the emissivity of the glass and how much heat gain goes through it. And so they put these coatings on in the factory in a vacuum, and they do it in a couple of times. And they have what they call different layers and cost of these coatings. And you can get ones that are called low G, or low solar heat gain coefficient, SHGC, that's the number they use, or low solar factor. They all mean slightly different things, but they all kind of, for every normal person, not a building scientist, they all mean in fact the same thing, right? So if you think about a single piece of clear glass, it has a solar heat gain coefficient or solar factor around 0.8. So that means 80% of the sunlight that hits the outside of the single pane glass window comes inside and makes the house warmer. And if you switch to 2 panes of glass and don't put a coating on it, you might hit something like 0.7, because it has to go 2 thicknesses of glass, less heat comes through effectively. You can then add a low E coating on that, and you can still get like almost 0.7 actually, or you can tweak that coating to get you down to like 0.4. So only 40% of the sunlight that hits the outside of the window comes inside. And you do that by putting the coating on the inside face of the outside pane of glass. And what happens is the sunlight comes through that glass, hits the coating, and a lot of the heat bounces out. But that heat's in the form of infrared rays you can't see anyways. And then the light comes through, the natural light you think of. So down to about 40% solar heat gain coefficient, 0.4, you can still have windows that look clear. They don't have a color, at least one an engineer can see. Maybe an artist can see a slight tint, but I can't. So they look like normal glass. So you're not giving anything up, except you're getting less heat in. Now that window will be 10, 15% more than one without that special coating. So you would only want to do it on the windows that matter, or, that kind of thing. So on a big apartment building, we'll often use those on Western facades, right? We'll use these low solar gain coefficient glasses. You can get down to 0, right? You can buy opaque glass where no light comes through, and that obviously lets no heat through. But you can get down to like 0.2 or so, where you still get, like in an office building, that might be something you choose, where the wall's fully glazed, which is stupid, but it is what we do. And then you use tinted glass, which cuts the amount of sunlight coming in, so it helps on computer monitors and stuff. But typically in homes, we don't like to put tinted glass in because people don't like it. You get this weird sunglass effect, like when you take your sunglasses off and it's blurry. So if you have a window, if all your windows in a room are tinted to keep the heat out, and then you open a window, you get this glare effect, and it's not very pleasant. So we don't tend to do that very often. So yes, so if you want to reduce the gain through your windows, the first thing you do is use external shading. It's often the most effective way. If you have north-facing windows, overhangs are the easiest choice. Other orientations, you need to use shutters. And then you can impact the solar heat gain coefficient of glass. What we didn't talk about with these low E windows is, in addition to letting less heat through, less solar heat gain, you can get that. But you can also get, when you go to low E coatings, they have this low emissivity effect. And that means that they insulate better. So you can get really good double glazing now that's effective as like 3.5 panes of glass if you pick the right low E coating. So there's a huge range of low E coatings, from inexpensive pyrolytic low E's all the way up to these soft Louis coats that are low soil leak gain coefficients. And so you can get R values of around 1 for double pane glass, the very best double pane glass in New Zealand. And one of the good things about not making glass in New Zealand is we buy the best glass from the whole world. So unlike some of the Aussies that so they used to not be able to get really high performance glass, in New Zealand we've always been able to have the best glass around. So when Passive House first got started in New Zealand, it was easy for us. It was really hard for the folks in Australia because they didn't have access to the same stuff we did. So it's always this balance between, because if you pick this glass that lets less heat gain in the summer, that same glass has less heat gain in the winter as well. So now you don't have the benefit of that gain. So we often try to design our buildings so we don't need to use low soil heat gain glass. But if we get a design in that's got lots of glass in it and the owner's like, no, this is what I want, we'll often go to that step. But it does mean more heating in the winter.
Now, just thinking back to that brand study that I talked about earlier, there's some other things that they talk about as factors of overheating here, and it'd be interesting to get your ideas about this. So they talk about carpets versus hard flooring, increased mass levels. What do those two things have to do with it all?
So thermal mass can definitely have a benefit. So if you think of a house with all the walls and mid-floors and everything are all concrete and all the insulation's on the outside of the building, like a very traditional passive house from Germany, so that building has a lot of thermal mass, and very good insulation in this particular case. So when the sunlight comes in, it first has to heat up the whole building, including the mass inside of it, so it takes some time. And then if you've got night ventilation to cool down at night, then it can cool down that mass overnight. Unfortunately, we've had buildings where they put good mass in them here in Auckland. And one of the examples I showed at the Building Science Summit a while back was an example of a building in Auckland where the clients contacted us after it was built. And they asked for a passive house, and what they got was a passive solar house, which was not modeled in any way. Unfortunately, a passive solar house can be modeled, and it wasn't. So that building overheated to the point it was unlivable. So she would move out in the summer. Because even with the windows open and the curtains down, and she had big doors to open up a ventilation, it just was unlivable in that building. So we added air conditioning and some additional shading for her to make it habitable. But the issue with mass is that it's not something you can change easily. In this case, she had a building which had inappropriate glazing and inappropriate glass specs as well, and a very heavyweight structure upstairs. So that would then get hot, and she couldn't ventilate the heat away at night in Auckland. So she had a building that just cooked all the time. So we've had designers, Rafe McLean down in the South Island's a really good example. Through his design practice, I've only seen a few of his examples, but his designs from 20 years ago are very heavy mass buildings, rammed earth, that kind of stuff. And he's moved from that to a very lightweight building, well insulated, well designed and considered for overheating, that you can use a little bit of cooling in. Because that building you can easily move around to be where you want, whereas the massive building is going to sit wherever the hell it wants to, and you can put a lot of energy in to move it. Whereas a lightweight building is going to sit, well, if you put a little energy, it's going to sit where you want it to. I've just got a lot of issues with people who use mass in buildings. To me, it's just an excuse. Like they'll say passive solar and it's got a concrete slab for mass and that kind of thing, and I've used dark carpet in the windows. So I lived in that passive solar house built in the 70s here in New Zealand, and it was 30 centigrade in the afternoon and 10 at night. So it was 20 degrees on average in the day, so it was perfect, right? And the designer of that home had his heart in the complete right place. I knew the architect quite well, and he designed the best home he could with what he had for knowledge to him in those days. And it was, if you put a lot of energy in, it was a comfortable house. If you didn't pay a lot of money for heating, then it was not very comfortable.
So do carpets make much difference?
No, sorry. That's just silly. So with more advanced computer models, you can look at the effect of carpets. And if you have a building that you're going to allow to oscillate a lot, so in other words, you're going to let it get cold at night and hot during the day, then carpets can help because the sun that comes in can heat the concrete slab directly instead of heating the air and then going through the carpet to the concrete. So there is some effectiveness there that can happen. But those only work, and passive solar only works if you're willing to deal with 30 degree in the afternoon and 10 degree at night, because then the house can use that thermal mass to heat and cool, because energy only moves in the thermal mass when there's a temperature difference or if the sunlight's directly on the concrete. So those effects, they're real, but they tend to be small, and they tend to only work if you want to be very uncomfortable in the house over most of the time.
Now, you were mentioning earlier something about that's happening in Wellington where the government is working with social housing providers and looking at getting some sort of a requirement for limiting overheating. What can you tell me about that?
So there's two stories that I mentioned. One was, so social housing providers are trying to do the right thing and get units for their tenants that'll not overheat. So there's that one we should talk about, as well as a separate one with building code, with district planning in Wellington City Council, which is an issue. But so the upfront issue is that social housing providers in developers are being asked to build and lease units to build to social housing providers. And some of the requirements they have there for overheating are well-meaning but not very good. They're having unintended consequences. So a typically thing they might say, well, it can't get over 26 centigrade for more than 4 hours in any apartment. And what I'd like to do, because these are meant, they're social housing, meant for very low cost, and they're meant for people who don't have a lot of money each month to spend on things, is I'd like those apartments to work well without any cooling and very little heating for most of the year, or actually all the year would be nice. In Wellington, that's pretty easy to do because our climate's relatively easy compared to even to Auckland. So I'd like to design those apartments to have low solar leaking glass on the western sides, on the northern sides to have overhangs, like that kind of thing. Design big opening windows. So they're maybe 10% opening. They don't have stays. They're actually pivot windows. So they've got big openings. So they can get a lot of air through the rooms, right? So they can easily be comfortable in those spaces, have bedrooms well below 26 degrees centigrade at night so they can sleep easily, with the offset that they have to trade some noise for that ventilation to stay cool. But that's a trade they can make. But if you have this requirement for 26 degrees centigrade at any 4 hours, it means you have a heat wave in the middle of the day. If it's 30 out, which can happen in Wellington, doesn't happen very often, but it can happen, I can't keep those apartments below 26. So the developers either got to carry the risk and say, well, they're going to complain and I'll put cooling in the apartments they complain. Or I'll put cooling in every apartment, in which case I'm not going to put Jason's low solar leaking glass in because it costs 10% more. I'm going to put a heat pump in anyways. Like I'll just put in this regular Bacom stuff. And I'm the same thing with external shading. I'll take the external shading off and save money because overhangs cost money. And I've got to buy a heat pump anyways. So the problem is that, in my opinion, it results in the developer and the design team to either have to take a risk or just put cooling in everything. And that kind of bridges into the next story I was telling you about, which is Wellington City Council, their district plan has a requirement for noise control in the central city, actually pretty much the whole city now, which implies that you need to have cooling in everything. If you're trying to do low-cost housing, people often won't run cooling. I mean, I know I've heard people joke about people turning off even ventilation systems in their apartments and causing mold problems because they're trying to save on power because, people live in these houses, they're smart and they're trying to do the best they can with their lives, right? So if they're not going to run cooling, and that's certainly what you see overseas as well, is people in low-income housing, they just won't run cooling. They'll just be hot, even if it kills them. I'd rather we had the ability to design passive cooling measures in these buildings, even if means that there is some noise problems. And the way we can do that is you still need a requirement to prevent people from doing dumb shit, because we kind of opened this session with, what do I think the problem? I think the problem is really bad design and not modeling stuff, right? So what I recommend to council and what I've recommended to developers throughout the country is that they use a standard called TM59 by an organization called SIBSE, which is the mechanical engineers of the UK. So in the UK, they've had this overheating problem, especially in London, and it's been dramatic because they have very high insulation standards, much higher than New Zealand, even though the climate's the same effectively. They've had significant overheating problems in London. And it's not driven by insulation. It's driven by, again, poor design, poor orientation, poor glass selection. It's pretty obvious what's going on. So the problem is they have the same issue as well, is that the developers there want to make sure that their clients don't have buildings that overheat. But engineers are liars. Let's just be we all lie. I'd like us all to lie the same way and consistently, so it then becomes the truth. So we need engineering standards we can count on. And TM59 from SIBSE is the one that's used for overheating for residential buildings. So what that standard does is it requires a relatively complex computer model, unfortunately, which looks at window opening area and airflow through the building. So if you have doors shut at night, internal doors shut at night, and there's a crack under the door, the air flows under the door through the crack, it takes that into account. It looks at solar gains for the building, the glass, internal heat gains, all that stuff's very tightly controlled so that you get 200 different engineers to model the same building with the same inputs, they should get the same outputs kind of thing. And that has two criteria. One is that the bedrooms stay below 26 degrees centigrade except for 1% of hours of the year, and that the living area stays below this adaptive thermal comfort criteria, which in Wellington would be 28, I think. And that's only for the hottest weeks. It's allowed to go up to 28. And that's because people adapt. If it's 26 for a week, you can handle 28. And if it's 15 for the week, you want it under 25. So that's how that's handled in TM59. And that basically says if you meet this criteria, it's okay to not put cooling in. If you don't meet this criteria, you have to put cooling in. And when we've modeled buildings in Wellington, we'll find that the top floor pretty much needs cooling. You just can't make it work otherwise. But the rest of the building, if we put in low solar leaking glass and we control our internal heat gains, we put the water heaters outside the units so they don't cook the units, and we put in more opening area than required in windows, we take into account the safety stays as well, then we can make them meet the criteria and they don't need cooling, in my opinion. especially for low-income housing. We've written a white paper that hasn't been released yet, but we've been trying to get folks to switch over to specifying that. And Kyanwater was requiring that for their large units here in Auckland, was Team 59 calculations.
How does modelling work when you've got a house that's got all these different rooms? And as you say, the doors might be open, they might be closed. You talked about this quite in detail in the Building Science Summit. What happens with those zones? How do they work?
We almost always start our designs, even for an apartment building that's got 300 apartments, we'll start with a single zone model. And what that means is, probably not old enough to remember check registers, but it's sort of like a bank account, right? If you have one account, you got your checking account. Basically, the temperature in the building is one number. It's one checking account for the whole building. Every apartment is the same temperature. And that's really useful to design the overall building and pick the overall glass spec and the roof and mechanical sizing, that kind of stuff. And the reason we do the single zone models is because they're very quick and inexpensive to build. And you can do lots of things and try lots of things without driving yourself batty. And then for a big apartment building, we'll always switch to a zonal model where each room in the building that can be kind of isolated thermally will be a separate zone. And that means that we can see that the apartments on the east side of the building heat up in the morning, but not in the afternoon. And the ones on the west side heat up in the afternoon, but not right. So you can still have big buildings that act as a single zone. So if you imagine a big office building with big floor plates, the people on the west side of the building do not feel the morning sun, right? But if you put a variable refrigerant flow system, a VRF heating and cooling system in, those allow you to move heat around the building very cheaply. In that case, we'll intentionally make the building act like a single zone. We'll cool the east zone in the morning and move that heat to the west side and heat the west side with it. So the whole building's at a single temperature. So that building, that office, this mythical office building we're talking about, we can use a single zone model, even though it's 20,000 square meters, because it's appropriate for the physics of what we're doing. But if you're doing an apartment building, usually you don't move heat from the eastern apartments to the western apartments. Like they each have their own heating and cooling system, and then it's not appropriate to use a single zone model once you get into the details of things. And it's pretty easy at that point to switch to a software that does zonal modeling. We tend to use Design Builder, Honeybee Works, and there's other tools as well. And they all tend to use Energy Plus as the modeling engine behind it. And you model the different rooms so you can see the different temperatures in the spaces. So you'll see the eastern apartments overheat in the morning, but by midday they're fine. And the northern apartments, because they get overhangs, don't overheat. And the western ones cook in the afternoon because the day's heated up outside as well as the sun coming in. So those apartments we need to put larger cooling in, maybe different glass is often a good choice. We could put sliding shutters in front of those windows. There's lots of design choices you can look at. Anyways, but those zonal models. As part of the Passive House Conference in Wellington last year, we did cooling like zonal and single zone models across a bunch of different topologies. So we did a couple different single family homes as well as an apartment building in different climate zones and looked at zonal models as well as single zone models and saw what the cooling loads were in those different spaces. And that's all. We've got that on our website somewhere if you want to look that up. But it's important that I'm really a proponent of using the simplest model you can at the point in the design where it's appropriate and then switching to something more complex later. Because if you do this other way around, if you bring the zonal model in at the start, you've got a big complex model where, like, often we'll run those models every 6 minutes of the year. So I've got 10 temperatures every hour of the year. So I've got 80,000 temperatures in every bedroom, and every room's different. And not only that, but it's actually modeling the relative humidity in the space, the surface temperatures inside of space, the radiative temperatures. Like, it's got all this data, right? But you can't look at it unless it's a research project because there's no client in the world can afford to pay you that much. So we tend to do these single zone models up front to get the building right. Then we do a zonal model to make sure we've got the cooling right, the cooling loads, size of mechanical systems if we need to. And then we're done. And that's quite an efficient workflow. That's my choice.
Jason, we're sort of moving towards the end of our time now. Can you just sort of give us a bit of a summary of everything we've discussed today? And just, if I'm a homeowner building a house today, what should I think about? What should I ask my architect or my designer and the builder? What should I be aware of?
I think the first thing to do is to realize that the people you're dealing with are not magic. They're people, just like you as a homeowner. So the builder and the designer and the architect, even the building science you're talking, they're all just humans, right? They know different things than you because they've worked in different areas than you have, but they're not magic. So they need to do work to understand the building. So the first thing I would say from my point of view is that if you're building a new house, it's a very expensive investment, and you should expect to know how the building's going to work when you finish building it before you start. So I would always recommend that you have the building thermally modeled before you design it, ideally early on in the design process so you can change the design to make it better before it's drawn up in detail and consented. But even at the consent stage, if you have to, you're better off changing the windows, changing the glass type in the windows, than doing it later. So I think If I was talking to homeowners, you should expect to understand how the building's performed, and you should have that written down with your designer. It doesn't have to be formal. I'm not saying you're going to do it to sue them, but just so you both understand each other. Like this client I talked about with a home that was overheating in Auckland, she literally told her design team she wanted a passive house, which to her had a specific meaning. The design team spoke back to her and said, well, we're going to give you a passive solar house, which to them meant they would make it have lots of glass and mass and hopefully it would work. Being a bit jokey about it, but they didn't model the building in any way. And the client asked for a building of high performance. She paid for a very high performance, but that building has a Zender. It's got a certified passive house ventilation system in it. It's got literally the design spec from her to the designers, of the designers to the window supplier was the best windows you can supply with the best glass you have. That was the spec. She didn't say, give me the most economical windows, or, oh, that's a bit too much. Can you give me something cheaper? She said, I want the best. And they gave her the best windows for a leaky old villa in Auckland. Like in a villa with not much glass and really good shading, that glass would have been the best glass to use. They didn't do it to be dicks. They did it because they didn't know any better. And the house is beautiful. She loves it in the winter. It's just not, it wasn't habitable in the summer when she got it. So I think that's the thing is make sure you're going to get what you expect and make it clear what you expect and make sure the design team does the work they need to make sure you get what you're going to get.
Jason, thank you very much. It's been absolutely fascinating hearing all of your experience coming through today. And yeah, I really look forward to catching up with you again soon.
Thank you.
Sharing knowledge is at the heart of our strategy to make buildings better for everyone. Sign up for our podcasts to learn more about creating healthy living conditions by protecting building structures from external and internal moisture damage. Thanks for listening. Looking forward to having you with us next time.